Okay, let's get started. So welcome everyone to this new talk in the GA webinar series on data science on graphs. It's my great pleasure to introduce Gonzalo Mateos today. So he got his bachelor degree from the Universidad de la República in Uruguay, and then his master's and PhD at the University of Minnesota in Twin Cities. And right now he's an associate professor at the University of Rochester, at the Department of Electrical and Computer Engineering, and he's also an Asaro Bigar Family Fellow in Data Science. He has been visiting many places, collaborating with many people on network science, distributed optimization, graph signal processing. For some reason, we don't have a joint publication yet, I think, but maybe in the future, that would be very nice. Applications that Gonzalo covers are, let's say, brain connectivity, smart grid, social networks, and so on. He will probably cover a few of these today. So it's a great pleasure to have Gonzalo talk today. So looking forward to it. So go ahead, Gonzalo.
All right. Thank you, Gert, for the kind introduction, as well as for the invitation. Same for Dorina and Toa. Thanks for running this seminar that I've enjoyed frequently. So very glad to be here, and to all that are connecting, good morning, good I don't know, afternoon or good night, whatever you are. So yeah, this talk today is about it's titled Graph Adjacency Spectral Embeddings. I'm going to talk about models, algorithms, and applications in the context of learning from network data. Before I get there, I just want to acknowledge and give credit to my collaborators, which I've been conducting this work. They're all from my alma mater in Montevideo, Uruguay, Universidad de la República. Bernardo is a PhD student I'm co-advising with Paola, and Marcelo and Federico have also been working with us actively in these projects. So thanks to them, of course, and credits to them for this work as well. So I guess the GAS seminar series, right, deals with data science and graphs. So I believe I don't need to spend a lot of time for this audience in trying to motivate, right, and acknowledge that, of course, we know there have been huge developments and advances on learning from structured data, grids of all forms in 1 or 2 dimensions, time series images. And of course, the road is not as smooth, but interesting, of course, nonetheless, as we start to try to accommodate network data that exhibits complex relational structures, right, arising in many applications and domains. Several challenges, of course, in taking that transition to learn informative representations that facilitate downstream tasks, right? Well, this particular talk today, it's going to be about a class of spectral graph embeddings, which are rooted in a very simple generative model for network data, and then the paradigm of graph embedding basically deals with starting from a graph, just try to obtain a mapping, right, a representation of its nodes in a Euclidean space in a way. So object that has no geometry at all, then to map it to a Euclidean space where we can leverage or bring to bear tools of geometric data analysis to do, I don't know, for instance, dimensionality reduction, visualization, classification, prediction, and what have you. Okay, so then the outline of my talk, I'm going to start talking about and introducing that model, namely random dot product graphs and the associated embedding problem that arises in that particular case. Said embeddings are known as adjacency spectral embeddings. And then the second part of my talk, I'm going to be looking at some aspects of algorithmic issues, how to, I don't know, compute those embeddings when there's missing data, when you have streaming graphs, and what have you. And if I have time at the very end, I'm going to highlight an application that we've used these embeddings and then these models for, namely online change point detection for streaming graphs. Okay, so then let's get started with the very basics. What are random dot product graphs? Let's take a look here as a generative model for random graphs. This is a very simple and tractable, I would say, a latent position model. So then we're going to be generating graphs on NV vertices, which are unweighted, undirected, and then they have no self loops. And the basic premise here is that for each node in the graph, we're going to assign to each a latent position or a vector in some latent space that's RD, okay, where D is the dimension of the embedding space, is typically much smaller than NB. So then, given these latent positions for each of the nodes, x1 up until xnb, then what the RDPG model specifies is that if you are focusing, for example, on the edge between I and j, potentially the entry in the adjacency matrix Aij, well, that's given by a coin flip, right? 0-1 outcome, edge or non-edge, whose probability is given by the inner product of these latent position vectors corresponding to each node, right? And then, of course, we impose symmetry and the fact we don't have a self-loop. So then, in a way, that induces some geometry that you can start thinking about. We're going to see through various examples, nodes that, or position vectors or latent vectors that are collinear, then give more a chance of these nodes connecting, whether vectors that are orthogonal, then or close to orthogonal, then are less likely to connect. They have less in common. In a way, that's what this module is capturing. So then it's going to be useful for us to just collect all these latent vectors, one per node in a matrix X, which has NB rows and then D columns. That's the dimension of the embedding space. Okay, so then that's the generative model. Let me just put this in context of other models just to argue on its expressivity. Of course, the simplest random graph model is an Erdős-Renyi graph. Then if you start to think about mixtures of Erdős-Renyi graphs, which of course are very simple, then you get stochastic block models that allows you to capture or explicitly parameterize communities, right? And then mixtures can be surprisingly flexible, as it turns out. And in particular, it's not hard to show that with RDPGs, you can subsume or capture SVMs. It's a matter of just having a position vector for each representative of each community, and then you design those vectors, the representative of each of the communities, so that then you get the corresponding connection probabilities in a way. So then that can be done. So then RDPGs subsumes SVMs. And then because we know that with SVMs, you can arbitrarily approximate arbitrary graphs in the sense of the cut metric, right? Well, of course, provided you can have a lot of blocks, and exponentially many blocks, but still in a way with RDPGs, you can model a lot of graphs. It's kind of an expressive model because of these reasons. All right. Now, that's fine. We can generate random graphs given these vectors. Well, the focus of today's talk is more on the inverse problem or the embedding problem, right? If you are given a graph, namely through its adjacency matrix that we assume adheres to an RDPG, well, the embedding problem is to find the best nodal positions, let's say, to obtain representations, the vectors x1 up until xb for each of the nodes. And of course, because we have a simple probabilistic model, right? Well, because of theoretical properties, a maximum likelihood estimator of the latent positions is actually very well motivated, but then it becomes intractable for large number of vertices. It's hard to solve this problem. That's clearly non-convex, right? Well, instead, we can just think about the connection probabilities, right, for each pair of nodes, these Pijs, and collect them in a matrix P, which is NV by NV. Of course, the RDPG model, because of the inner product definitions, right, specifies that the matrix P is low rank, it has rank D, and it's positive semi-definite and can be factorized as X transpose, right? That's the idea. Now, notice as well that if you have an observed graph A, then that's clearly a noisy realization of matrix P in the sense that the expected value of A is actually P, which suggests a least square regression approach to try to find an X matrix, right, such that X transpose is close to A in the least square sense. So then we just have a low rank factorization problem to recover those latent positions. And then, as you know, the solution to this type of problems is actually straightforward. It's given in terms of eigenvectors and eigenvalues of the matrix A being real symmetrics. It can get decomposed with eigenvectors U and eigenvalues lambda. Now, if we just keep the top D positive eigenvectors and the corresponding eigenvalues, well, you know that the best rank D PSD approximation of A is given by those truncated eigenvectors and eigenvalues. Indeed, what's known as the adjacency spectral embedding basically is to just retain those top D eigenvectors and then scale them with the square root of the top D positive eigenvalues. That's the so-termed adjacency spectral embeddings, and then that gives us the best rank D approximation that's positive semi-definite to matrix A. Okay, so then the columns of X ASC are the corresponding nodal embeddings. Well, something worth noting, right, is that the solution is not unique, right? Because if you just rotate those latent positions, then inner products are not affected at all. So then we have an inherent, right, rotational ambiguity, and then all we can claim is that the problem is identifiable modular rotations. Then the most we can hope for is just to obtain these up to rotations. Okay, so then that's the ASC, spectral embedding, to obtain the latent positions in this particular context. Now let me give you a bunch of examples just to see a little bit more in terms of the properties of the embeddings in this particular modeling context. So then just a toy example here, we have an SVM with 3 communities in 1500 nodes. These are the parameters, the connection probabilities, and then the probability of drawing nodes from each community uniformly at random. Here on the left, you have, of course, after reordering nodes based on the memberships to communities, what would a sample adjacency matrix look like? That's my data that I want to then embed the nodes. And then if you do an ASC of this matrix A, the reconstructed P hat, an estimate, right? X hat ASC, X hat ASC transpose, then looks pretty accurately like the matrix of probability SPI. And then the right-hand side, you have a 3-dimensional depiction of the corresponding embedding vectors. Then, as you would expect, right, they cluster in 3D space, representing memberships to communities. And you can see, let's say, once you go from here to here, now here you can bring to bear methods of geometric analysis, like, I don't know, to visualize, to cluster, and so forth. So then we can work here more comfortably, or if you want, just for the sake of background compatibility with standard machine learning pipelines, when you can embed vectors there, okay? Unless you want to do GNNs and stuff, which is fine as well. Now, another nice property of ASC embeddings, right, is their interpretability. And then let's go back again to another toy social network, Zachari's Karate Club, which has 34 nodes, members of a karate club in Indiana University back in the 70s. We know that that's a club actually split in 2. Half of them follow the instructor, half of them follow the administrator who got a fight. Well, here are the community memberships, color-coded in blue and red. And you can see now, as I'm plotting the embeddings into the space for d equals 2, the ASC embeddings, well, we can see some interesting properties, right? On the one hand, the vector magnitudes, right, tend to indicate how loquacious are, in this case, the nodes, how actively they are in establishing connections, or how central, if you want, based on connectivity within communities, right? So then you can see that the instructor and administrator, 0 and 33, have a very high magnitude. They're very central and connected to most nodes in their communities. And then what's important is also the vector angles, right? You can see an alignment at 90 degrees of 2 clusters, right? So then vectors or members of the same community tend to align, because then if they're collinear, the probability of connecting is higher, and then their position in latent space tends to reveal communities, right? So then the angles are important. Notice how they form almost 90 degrees here, the blue and the red dots, because there's not too many connections across communities, and then within communities, they tend to be collinear. And then the magnitude tells you also how strongly they connect within their community. So then that kind of geometry is induced based on the linking probabilities being given by inner products. And then that's nice as well and interpretable. Now, I like this graph very much, so that's why I'm bringing this example here. That's a mathematics collaboration network centered at Paul Erdős, and then nodes are mathematicians. They're connected, they wrote a paper together. Again, Paul Erdős was very well known for his social approach to mathematics and organizing parties, collaborating with many people. So then very central, very connected. And most mathematicians tend to have an Erdős number, namely their distance to Erdős in this collaboration graph, of at most 4 or 5, kind of a 6 degree of separation result in this context. Well, here people have looked at this co-authorship graph where they just restrict to the mathematicians, which are 4,000 of those, which have an Erdős number of at most 2, right? And then here's the corresponding adjacency matrix, no kind of discernible structure if you don't find that structure somehow. And then, well, that community structure can be revealed after assigning labels based on a following embedding clustering approach I'm going to describe. And then if you do that, then here's what you get, where the community structure becomes apparent. Those are the same thing, just after permuting rows and columns, but then structure is apparent here, it's not over there. So then what did we do here? We just obtained the ASC embeddings of this adjacency matrix over here. And then we performed, instead of a standard k-means, as you would do with standard spectral clustering, right? Here, what makes sense to do is to do angular k-means, right? So you try to cluster nodes if they are kind of closer, kind of share, they tend to be more collinear than others. So distance is not the issue here, it's more like collinearity, and then you can do that to reveal structure in this particular case, okay? Now, finally, you can also study maybe dynamic graphs, and then more on that coming up later. But here's a dynamic graph G of T, a snapshot of adjacency matrix of international relationships among different nations. Nodes are nations or countries, and then edges in the dynamic graphs are assigned if the two incident countries actually had an alliance treaty during a particular year, right? So then here what I'm showing is I'm tracking the angle between the representations based on ASCs of the UK and France, going all the way back to the 19th century up until now, the turn of the 21st century. And then things you can see that the measure here is the angular difference, right, as a function of time of the two embeddings. If they kind of become more collinear, is that they're closer, they have more treaties. If they're more orthogonal, is that they are not as close. And you can see that back in the day, kind of orthogonal during the late 19th century over here. Then they came closer during the World Wars, as you can see, and there was a retreat, right, during the German invasion of France. Clearly, they kind of were not as aligned at the time, and now they became very, very collinear. As you can see, the angle coming to zero in the run-up to the European Union, kind of interesting. I don't know what happened here, really, the kind of a retreat, but anyways, that's for those that know more politics or history of Europe than myself. But again, interesting things you can do with this embedding just by means of these examples. Now, I want to focus a little bit on something that we've been working on our side from a modeling perspective. So far, we talked about RDPG models, or its vanilla version for unweighted, undirected graphs. For digraphs, the extension is natural. Then you're going to have two vectors per node, right? One capturing the inner connectivity, the other one the outer connectivity, and which you can embed using an SVD of A if it's directed. Now, the question, what if you have weighted graphs, like let's say some weight map that specifies what are the weights, the entries in the adjacency matrix? Well, our idea is to say that latent positions are in some way, in this context, when you have weighted graphs, related to the moment generating function of the weight distribution. More specifically, for each node, what we have now is a sequence of latent position vectors, let's say all of them in d-dimensional space, indexed by m in the naturals, such that then if you are looking at a specific weight between, let's say, node I and j's, then the moments of that weight are given by inner products. Let's say the mth moment is given by the inner product of the mth latent vector of node I and the mth latent vector of node j. So then the MGF is given in this particular form. You can see then that you can recover, of course, the vanilla RDPG by setting all these latent positions to be the same, right? Because in the Bernoulli case, then all the moments are the same, they are equal, and then you can recover them with a single inner product. When you have more complexity in the distribution, right, then you need more of them. Now, different from existing extensions to weighted graphs, right, they mostly relied on a fixed known parametric distribution for the weights, right, which is kind of limiting because you need to know what this distribution is at the outset. Typically, it's the same across all edges, which is maybe, again, too restrictive. And typically what it says that they have a parametric distribution. The parameters maybe could be m, and then each of them are given by inner products, let's say. And then again, you can recover the vanilla RDPG model if this distribution were to be a Bernoulli theta. So then you need a single parameter there, and then that parameter is given by the inner product of the xi, xj's, let's say. So then that's a particular case. Now, how do we perform inference in this context, the embedding problem? Well, you can estimate, right, the mth latent vector kind of the one that explains the mth moment of the weight distribution, by doing an ASC of this particular matrix, where you just do the entry-wise product, right, of the adjacency matrix with itself m times, right? Because then you want to decompose the matrix which has the entries aij to the m. So then you can do that as follows. And let me show you an example of kind of maybe the merits of this representation in terms of discriminating a different type of structures or recovering rich structure in different graphs. Here's a toy graph, just for the sake of illustration. We have a 2-block weighted stochastic block model with 2,000 nodes, where edges are determined just at random by flipping coins with probability 0.5, but then the weights actually change. Kind of most weights are Gaussian with a mean 5 and standard and variance 0.1, except among the second half of the nodes from 1,001 to 2,000, and then weights among those nodes, right, are just Poisson distributed with rate 5. Okay, so then all the other weights between the first group and then across groups are Gaussian. For the red cluster of nodes, then the weights are Poisson 5, and they have the same mean. So then here are the ASC estimates, right? Xi across nodes I hat for different m equals 1 over here, 2 in the center, and then 3 on the right. So looking at first, second, and third moments, where the embedding dimension is 2, and that makes sense because we have 2 communities, so it's a rank 2 connectivity matrix, right, for this case. Notice, right, that the embeddings are indistinguishable for m equals 1 because they have the same mean, right? So then clearly the embedding points are centered in both cases at 158.0. So then nothing to be discerned here. Now in this toy graph, we can explicitly compute the embeddings forms, the embeddings analytically for kind of all m, and then for m equals 2, even though you see that they should be kind of separated, still because of noise, it's kind of hard to tease them apart, right? If you didn't have the colors here, and then you just have all these point clouds, you want to say what's red, what's blue, it's kind of hard. Then if you go to m equals 3, then you can start to reveal higher structure because the skewness kicks in, and then you can separate them nicely, let's say the Gaussian from the Poisson distribution in this particular context. And if you were to classify or whatever, then again, it's interesting to go to higher orders than to see this particular information. So then we don't need to compute, of course, all infinite embeddings in general, but then it's for up to us to actually choose where do we want to look to reveal this complex structure that now has an additional layer because of the weight distribution. That's kind of the idea of this non-parametric model. Now, interestingly, we can establish consistency of these ASC estimates in this particular context. Suppose that B, just to give you a flavor of the result, B is a NB by NB random, symmetric, and hollow matrix. The entries are independent. Their mean of B is this P matrix that can be factorized as XX transform for some X matrix, which is NB by D. So rank D or lower. We assume that we have bounded weights or entries in the matrix B with a uniform bound M for some positive M. And we also require a spectral gap or separation condition on the matrix B, which we assume to be of rank D. And then the eigenvalues are distinct and positives. And then we have a gap, let's say, from the smallest positive eigenvalue from 0. And then the minimum distance among eigenvalues has to be bounded depending on some delta and the number of vertices you have. So you have a spectral gap condition, which is kind of typical. Well, in this particular setting, we can show that the ASC of said matrix B, if D is the true D is known, is actually consistent in the sense that almost surely you can find an orthogonal matrix W such that the estimated ASC embeddings converge in probability at this given rate to the true embeddings, right? Even if you have, of course, weights. And then what's the upshot of this general result for RDPG inference? When you have weights, well, this implies that if you pick for each M, right, B to be this matrix AN, which is given by the entry-wise products, that's what we needed to obtain for the different values of M, the embeddings correspondingly, well, you can recover the true latent positions as the number of nodes goes to infinity. And again, that's kind of a nice property to have. So just to summarize what we've seen so far in terms of RDPG modeling, well, this is a simple model, has some nice geometric properties, has been very useful in understanding spectral embeddings in general. And there's other latent embeddings, of course, like MDS, like Laplacian-based embeddings and so forth. So then this is just one of them that has been widely used and studied. In terms of expressiveness, right? Okay, it's kind of, it can capture a nice graph structure because SVMs, which we know are useful to some extent, are captured as particular cases of RDPGs. Now, it's a special case of more general latent position models introduced by Hopf back in 2002, where now, in general, right, connection or linking probabilities can be given by just some general linking function, let's say that's symmetric on its two arguments, right, this kappa function here, and not necessarily an inner product, right? And then the corresponding linking matrices or the kernel matrix K that results when you evaluate this on all pairs of latent positions, okay, can be, even though it's of course a particular case, right, it can approximate an arbitrary kernel matrix if you have a large enough D, right? And then because of Mercer's theorem as well, you know that with inner products, we can, even if we have infinite dimensional representations, we can recover an arbitrary kernel function. So in a way, it doesn't get you there, but then if D is large enough, you can get to arbitrary linking functions you could potentially have, and then that's nice. Now, in terms of plausibility or adequacy of modeling real-world network data, well, there's been some questions that have been raised recently. In particularly back in 2020, people have shown that it's actually theoretically impossible that then on models that have infinite dimensional representations D and based on inner products, you cannot generate sparse graphs that at the same time have high transitivity, high density of triangles, which we know are very common in social networks or social graphs. You cannot have both these two things. That can be maybe a limitation of the usefulness of these particular models. However, actually last week, a paper came out that you can, that has shown that one can have both those properties if one allows the embeddings D to go to infinity. So then you have latent positions in infinite dimensional space, and then the points actually live in a low dimensional manifold, okay, within this high dimensional space. In that case, then yes, you can recover both of these structures, kind of not everything is lost. So then, yeah, I invite you to take a look at this very recent paper that came up last week, if you want to know more about that. So then that's all I wanted to say in terms of models. Now, next, I want to just discuss a little bit of, algorithmic advances. We've been actually exploring very simple algorithms just for the sake of, I don't know, gaining in scalability, gaining, I don't know, being able to work on more general settings, namely online streaming settings and so forth, while yet being able to efficiently obtain these embeddings for various applications and timely ones. Okay, so what are some I would say maybe challenges faced? Well, these spectral embeddings, right, rely on eigenvector computations. And then when we're looking at most of the works and then what they were doing, well, a state-of-the-art package for computing ASCs is Graspologic, that basically relies on just the Python functions to obtain eigenvectors, let's say. And these are kind of efficient, but still for large graphs, really, you cannot just rely on those. And we were surprised that there was nothing else in terms of trying to obtain a more efficient computation. So there's questions on scalability for large graphs. Now, what if you are dealing with sequences of graphs and then you want to track the embeddings as they evolve in times? This is also going back to the formulation, right? The ASC, in a way, as it fits matrix A to XX transpose, it's in a way introducing some biases, right? That's really not what you want to solve, because for hollow graphs without self loops, we know that A is going to have zeros in its diagonal, right? So then if we try to fit A to XX transpose, well, in the diagonal, what we have in XX transpose is the Euclidean norm squared of each of the latent positions we want to estimate. So then we're trying to force them. If we focus on the residuals in the diagonal, we're forcing them to zero, introducing bias. And that's really not what you want to solve. Okay, the ASC problem becomes simpler, but then it introduces some biases. So then it's better to actually introduce a mask matrix M that in a way is neglecting the residuals, right? So then that's a better formulation, and we can see how we can solve that in a second. There's been some iterative procedures that basically iterate between finding an ASC, then is subtracting the diagonal and then repeating again. But then these methods, while being complex, because each time you correct the diagonal, you have to recomplete an decomposition, then they have also shown that they can exhibit cycles and not converge. And that's not great. While again, some heuristics I don't know, can work in some cases. So we are thinking, what about using just, I don't know, simple gradient descent? What about non-convex first order methods to solve a problem like this one, right? As we do in matrix completion or in other contexts, can we get scalable algorithms in this particular setting? And also, if the moment you introduce a mask to actually remove residuals in the diagonal, then this clearly opens the door for accounting for missing data. If you don't get to observe the whole A, but you only have a few samples of it, then can you still find that low rank decomposition? Well, conceivably you can, because you have enough degrees of freedom if D is actually small enough. Okay, so then we're going to look at that as well. So then the goal of this part of the talk is just to develop algorithms for a general RDPG inference or embedding approach, right, that offers better representation by solving a more suitable problem, let's say, at lower computational cost, scalability, right, and in more general settings like missing data and when you have dynamic graphs that potentially could be streaming, right? So then, as you said, we just thought, why not go to very basics, right, and maybe consider just the following objective function, as we said, where M could be a diagonal removal or just in general missing data template of what you have and you don't have, which is clearly non-convex with respect to X, but is convex with respect to XX transpose, right? And then let's apply gradient descent to this particular problem. In this context that people have looked at it, of course, matrix completion, matrix factorization, it goes by the name of factorized GD or procrustes flows. The iterations are quite simple, right? You can compute the gradient explicitly, this is smooth, and then you can even show that if you start close enough, then you have linear convergence to the global optimal solution. Okay, so then you can find that it has a kind of benign optimization landscape where most stationary solutions are not global optimal. Okay, so then this has been widely studied. A nice tutorial or overview in PSP of this kind of problems you have a reference down here. Now, let's see how this works numerical in terms of scalability. Here we have some runtime comparisons where we compare this GD approach with the state-of-the-art graphologic SVD computation in Python for graphs that go all the way up until 25K nodes. It's really much faster and scales more gracefully. It's not as great if you have a random initialization, let's say for the GD iterations, but then we tried maybe a smarter initialization based on a sketch randomized SVD, which is kind of fast to obtain a ballpark initial solution, and then with that the scaling is much better and even faster. We also derive some gradient descent type of algorithms as well, which the results are not shown here, but then the scaling is even faster, and then we are just writing this down for an upcoming publication. But again, using gradient descent makes a lot of sense beyond just eigendecomposition as people have been doing so far. Now let me just talk a little bit about missing data as well. Here we have this simulated data example. It's a bipartite graph that simulates a two-party senate, okay, where nodes are 50 senators as well as 230 laws. Parties submit their laws, and there's some bipartisan laws. And then when you have a partisan law, then the supporting parties more likely to support or vote for that law. In bipartisan law, then things are more even. And then edges in this bipartite graph, let's say IJ is going to be in the edge set if Senator I voted for or supported Law J. And with that, we can generate a synthetic data set. Now, in terms of introducing missing data, we say that for each law, right, a subset of senators has 30% chance of being absent and then not voting. So then we have a few edges that we don't know what's going on. And then here you can see the corresponding ASC and embeddings for nodes, laws, and so forth. And then on the right, you have the corresponding gradient descent based or obtained embeddings, right? And then you can see there's clusters, the circles of the senators themselves. And again, they are kind of at 90 degrees. And then senators vote for a lot of laws, so then they are the most loquacious ones. Then you have clusters as well for the partisan laws, which are aligned with the senators. And then you can see here the bipartisan laws, which are kind of in the middle. That's kind of interesting and expected because of the connectivity structure. Now, on the other hand, if you do an ASC, right, here you have that the missing data senators, in a way, are their own clusters. So there's kind of these artificial clusters which are induced here. Whereas if you just model this as missing data and then you do a gradient descent based embeddings, well, the senators that tend to be absent are actually fall within the clusters of their co-partisan senators. Then it kind of reveals better the hidden structure in the data, even though there's some missing data. So it gives more accurate representations if you want. Of course, in this toy example, just to illustrate kind of what are the differences that you can gain from here. Now, what about dynamic networks, potentially where we collect graphs from streaming data? The goal might be, if you have a sequence of graphs, right? Maybe as we saw already in this network of international relations among different nations, we would like to track the underlying positions, the model, as new graphs come into picture, maybe to do some hypothesis testing, as we're going to see later on, maybe change point detection, what have you, in various applications, right? Maybe monitoring wireless networks, evolving social networks, evolutionary clustering, what have you, many applications, of course, of dynamic networks. 101 naive approach would be to perform independent embeddings. You get each slice, and then you can compute the ASC of each of them. But of course, that's not desirable, right? Because we would like to pull data together. It's computationally expensive to do eigendecompositions or ASCs each time. And then the most critical challenge here, right, is if you do this separately, remember, we have this rotational ambiguity, right? So then how do we align separate embeddings could be a problem, right? Because then this could be rotated arbitrarily if you do them separately. And then if you want to do a hypothesis testing, for example, just to check, do these graphs come from the same model? Well, if they're not aligned, then that's an issue. And of course, you can solve the alignment problem separately using reduced rank procrustes rotations, or there's other procedures, but then that's not ideal. It's computationally expensive. Then you want to do something else. And then what we propose here is something, again, very simple as well, building on our simple gradient descent iterations. If we want to compute the embeddings at time t, well, why not just do a few or maybe one iteration of gradient descent to refine the previous embeddings we have at time t-1. Let's say we use the embeddings we had before as warm restarts for the optimization in the next time interval, right? And then the idea is that if the dynamic graphs kind of change smoothly, well, that would, I don't know, you will start in the ballpark, and then hopefully you will have the alignment for free in a way, and then that's nice as well. So you could ask, right, when looking at this problem of sequential calculation of eigenvectors, right, isn't this again, a classical problem, maybe to update recursively an SVD or an eigendecomposition? Well, it is actually, indeed, I claim. But these existing more algebraic algorithms are in a way efficient for only specific types of perturbations. Granted, maybe you have a rank 1 perturbation, then you can update things efficiently and so forth. But nonetheless, as we see in this example down here, if you rely on those, and then this is one state-of-the-art approach to recursively update SVDs, you can still obtain, there's no guarantee of the alignment in a way, and then it tends to be not very robust compared to the GD approach. Then again, this is a toy graph. We have a SVM with 2 communities, where again, from time t=1 to time t=2, actually a node randomly changes affiliation. It moves from one group to another one. Then I want to recompute the embeddings just to try to capture that. And here you have the time 1 embeddings for gradient descent, and then the SVD calculation, and clearly they are not aligned the same, but again, that's our reference point. And the question is, given those embeddings, then how can I recompute the ones after the change, right? And well, here's what you get with gradient descent after using these ones as warm restarts. And you see an extra point here, probably that's the new node that actually moved. But from the most part, you can see that they are comparable, right? In this case, they were aligned, and then you can compare them at time to time. Whereas we don't have longitudinal, as people call them, stability in this particular case if you use the eigendecomposition update, because you see, okay, you have the 2 clouds, but they completely moved in the embedding space. So then you have to realign them, and then that might not be desirable in a way. Okay, so then that's something to take into account. Now, let me show you some examples of applications where tracking embeddings could be useful. This is a real data application of wireless network monitoring. This is data we had from a Uruguayan rural area school, small graph with 6 access points in a school. I think 3 of them are in a top story of, there's a 2-story building, 3 are in the 2nd floor, 3 of them are in the 1st floor. And we have hourly RSSI measurements over 4 weeks from which we we can decide on edges, and then we have these hourly measurements that gives rise to roughly 655 slices or graphs of these wireless networks. And then actually the administrator, because we use this graph later on for change points detection, we cherry picked this one because we know that somebody moved an access point actually for kind of in the middle of the interval at time 310, right? So again, that's not very important here, but just a curiosity. What do we find after performing embeddings using gradient descent sequentially in time? Well, notice that here again, I have two plots because this is a directed graph. So I have the in embeddings and then the out embeddings. I'm labeling them node 3, 5, node 4, 6, 2, and 1. And for each of them, I'm plotting the points in 2D space, right? As the embedding evolves in time. So then lighter colors means later point in the time horizon, where darker colors is where you start. So then this embedding here of node 4 fluctuates from here to here across time. That's the idea. And then things we notice, right, that's that the access points are basically in two clusters, kind of, they are radially aligned, as you can see, except node 4, which in a way maybe was bridging the two stories somewhat. It's kind of in the middle, right? You see that in time, you have mostly, for the most part, radial shifts, which means that most of the access points are not changing community, or kind of nothing changed to them. So they move, but they move radially. So that means that their community is preserved. Notice interesting that the access point 4, which actually was moved closer to the upper cluster, right? This one moves transversally in a way. So then there's something different there, which this actually can capture. And then that could be interesting argument. Now, this is another nice synthetic example, which we picked up from this paper that proposed a so-termed unfolded ASC to actually embed multiple graphs from a dynamic network while preserving some desirable properties, what they call cross-sectional stability, meaning that for a given time snapshot, then nodes that are kind of stochastically or equivalently or similar, then shouldn't be embedded close in latent space up to noise. Whereas they will also like to have longitudinal stability, namely nodes that are not changing in time, across time, then their embeddings across time should kind of remain also invariant. So then for a given time, nodes that are similar should be close, but you also want to have that across time, if nodes do not change, then they shouldn't change too much in time. So then these two notions was something that they wanted to have, which of course, independent embeddings might not have, because again, you are not imposing any type of coupling across the embeddings. And then another prior embedding for multiple graphs, which is called the omnibus embedding, as we show here, didn't have. So let me show you this example, right, that they cooked up, and we also tested our gradient descent approach in this context. So there's two SVMs with 4 communities, which are color-coded here. Their connection probabilities in pi actually changes from time 1 to time 2. So then time 1 is the first row, time 2 the second row here. In particular, what they simulated here is that community 1, the blue one, and the orange one, right, which are separate originally, then they merge at time 2 by changing the probabilities. And then community 3, the green one, slightly moves, but then community 4, the red one, maintains the probability. So then that one should remain invariant, right? So then, as you can see, if we embed those graphs, I have one at time 1, another one at time 2, then both the unfolded ASC and gradient descent exhibit the desired cross-sectional and longitudinal stability. In particular, cross-sectional stability, you can see that when the communities merge, you have the blue and orange points coming together. So you have that. And then longitudinal stability can be tested by looking at the red cluster that didn't change, right? So then the point should be in the same place from time 1 to time 2. So then you have that, and the shape is not changing in time. That's nice. On the other hand, right, if you look at the independent embeddings, it doesn't exhibit, for example, longitudinal stability, the red one. This is done separately, right? So then the red one, the red points actually move a little bit, so then you don't have what you want. Whereas the omnibus embedding, which is another one, actually doesn't exhibit cross-sectional stability because it's embedding everything together in a way. And then you can see that the orange and the blue do not merge, right? So then these points should be close in the second time, but they're biased by the first time. So then you don't have what you want, whereas GD is giving you that. Then what are advantages of GD over the UASC? Well, it gives a better representation because of the cost function we optimize, and you can see the cost values are actually smaller, so it represents better the given graphs. But also This is a batch procedure. The UASC actually puts all the adjacency matrix side by side in a very fat matrix, and then does an SVD. So it's a batch procedure, right? So then this method, ours, the GD-based approach, can actually deals with the embedding sequentially and times if the graphs were to be streaming. So then that's nice as well. Of course, granted, they have very strong statistical guarantees on the stability properties, which we haven't been able to prove yet. But then that's a nice claim they have in this new DIPS paper from last year, if you wanna take a look at it. Now, a final thing I wanna say about algorithms here is, what if you have a varying number of nodes? Okay, kind of an out of sample generalization of the embedding whenever maybe there's a node addition. Node deletions are easy, right? Just remove the embeddings from the matrix XT as new nodes come. So let's focus maybe in the case where at time t plus 1, a new node, let's say nv plus 1, joins the party. Kind of it's a new member in this graph. So then the new adjacency matrix, right, is an nv plus 1 times nv plus 1 matrix, which has an extra column and row of length nv. Of course, the diagonal element is 0, so it doesn't matter. So the question here is, suppose that at time t, I already have the embeddings of all the other nodes that were present there from 1 up until nv. Can I compute in a somewhat efficient fashion the embedding for the new node, let's say x hat nv plus 1, without having to recompute everything from scratch? That's what they would like to do. It's kind of, and again, you can think of it as an out of sample or inductive generalization or embedding in the context of computing these representations, right? If you're thinking more broadly in machine learning context. Well, a very simple idea, but nice one, was proposed in this work over here, and even before, which goes by the name of a least squares out of sample embedding. The idea, right, is to embed the new node as the least square solution to the following system here, right? Again, this is the data we're given. So then we know the new node to what, once we see the new graph, we know this row or column of the adjacency matrix of the adjacency matrix, excuse me. We know to which other nodes from the previous one, the nv plus 1 node is connected. So we have A. And we have the embeddings of the prior nodes, let's say all the way from 1 up until nv, right? Because of the RDPG model, the embedding vector, the dimensional vector of the new node, nv plus 1, then its probability of connecting to the existing nodes is given by inner products among the latent positions. Then if you look at this matrix product, matrix vector product, then what this is doing is, right, is telling you that the first entry in the adjacency matrix is given by the inner product of the embedding of node 1 and the new one and so forth. So then you really want to solve this system of equations to kind of capture that. And of course, we can do it in a least square sense to obtain this particular embedding. So that kind of makes sense. It's kind of simple and can be shown to be consistent as nv goes to infinity. So then this out of sample embedding gives you consistent estimates as if you were to solve everything from scratch. And it kind of preserves alignment as well, which is nice. Now, the problem, one could argue, again, if the focus is going beyond just one node addition, and then nodes maybe keep on coming, and you want to keep on doing this for more and more nodes which are added, well, this assumes that the embeddings do not change in time here, because nothing is done to update the old XTs, right? So then you just focus on the new node embedding, but then the other ones remain. And if you keep on adding nodes, clearly the positions of the other nodes could shift as well, right? So then you need to update those or refine them. And if you don't do that, error would accumulate if you keep on adding new nodes, which is undesirable. So then what we say, well, we could do here, right, is okay, keeping on with our gradient descent, a simple framework is, okay, if at time t we have the embeddings of all the prior nv nodes, let's update the embeddings of all nodes at time t plus 1 when we have some additions, right, by running one and a few iterations of gradient descents with a starting point or initialization, right? For the existing nodes, we use the embeddings we had so far at time t, the x hat t. And then for the new nodes that are coming in, we can solve this simple least squares problem to initialize these simple embeddings and then kind of refine everything from there, right? And then here you can see for a simple toy graph example, dynamic graph, where you have an Erdos-Renyi graph with probability p 0.1, and then across time, I think initially this has 1,000 nodes, and then as time keeps on going here from 0 to 1,000, then at each time point, a new node with the same linking probability is added, right? And then you can see that the gradient descent approach, if we look at the error on the embeddings, right, then kind of keeps is on check, right? It's fine. Whereas if you do this least squares without re-update type of estimation of the embeddings of the new nodes, well, eventually the error starts to drift because you have to re-update the positions of the other nodes, which is, again, kind of a non-adaptive solution. It's fine for a few nodes, but then if you want to look things in the long run, then you may want to think about re-updating those embeddings. So then just a final real data example here. The World Cup is coming up, so why not study a football network? That's a dynamic network, GT, of national football teams. Nodes are teams across time, and then we draw edges in these dynamic graphs. If the pair of teams, let's say I and J, play at least an official match during a time horizon from T-3 to T. So we look at windows of 4 years, so that then we have a World Cup always there to kind of, so that then teams mix up and we have some interesting graphs. And we have weights as well, kind of counting the number of times that the teams actually played over these time horizons. Then we start at where the first World Cup was held, actually in Uruguay, fun fact, back in 1930, where there was only 41 teams playing football back in the day. And then we finished at 2015, going year by year, where now there's more than 220 national teams playing, but you know, countries split, new countries join, so then there's no additions and deletions all the way. And we fixed D to be 7 because we know there's 6 confederations, right, that kind of clusters. And we do just one more just to capture, maybe have some robustness, let's say, if we're missing something there. So we're focusing on the connectivity patterns or the embeddings for the teams in 2 confederations, namely Asia and Oceania. And here you have the corresponding embeddings going all the way back to year 95, 2005, and 2015, which we obtained actually using our sequential gradient descent-based approach, and then kind of countries could, in the whole network, embedding the whole network, like where countries could join, disappear, and so forth. And the focus here, again, this was cherry-picked because we know that Australia, that used to play back in the day in the OFC Confederation, the Oceania Confederation, and that's what you see here, right? The blue teams align Asia, the green teams align the Oceania ones. Australia actually moved or switched confederation back in 2005. Okay, and then you can see that the method actually picks it up very clearly, not too much to 2005, but then 10 years after it really moved, while the other embeddings kind of remained more or less in the same location and aligned. So then you can pick up those chains while preserving alignment. And again, just a huge example of how this could be used to track structure of network data across time. So then, just in summary, we looked at algorithms to estimate latent nodal positions in RDBG. So kind of not a lot of new stuff here in the sense that this is just a good old non-convex matrix factorization problem. I argue that the impact here is in actually applying these techniques, first order methods with missing data in a scalable fashion in dynamic settings to network embedding problems, which haven't been looked at to the best of my knowledge. Things we are doing currently, and in the future, we're going to release all these routines, data sets, and so forth in our GitHub repository. The link to that coming up later. And also, I think what's of interest that I haven't seen in many works is to analyze a gradient descent in this dynamic setting, right? It's a non-convex, so then most of the results in time-varying optimization are for convex problems, but then non-convex are more challenging. One can look at the norm of the gradient that you accumulate across time and then see how that behaves. So then we're starting to look into that to see if we can say something interesting in terms of how this behaves or how solutions behave in this particular context. And I think that's an interesting problem looking forward. So then if I have 2-3 minutes, I just want to touch upon another application domain that we have been working on extensively in using these RDBG models, which is a problem of online or sequential change points detection. And again, the setting is kind of simple. Suppose we are given a streaming of undirected graph observations, AT, as you could have over here, that we assume can be modeled as random dot product graphs. the goal is to detect in an online fashion when the underlying model changed, kind of trying to do it as quickly as possible. And this, of course, could be relevant in many monitoring applications across various domains. And you can see here, right, you had a 2-block SVM, which eventually turned into a 3-block SVM. Can you, as you are getting a adjacency matrix, detect those changes kind of as fast as possible? And if I just want to summarize at least what I believe are the contributions and impact, is the goal is to marry sequential change point detection methods that have been widely studied, right, with the graph representation learning substrate based on ASC embeddings. Also, RDBGs are kind of explainable, so then this gives a little bit of interpretability for these real-time monitoring procedures, and with while providing some guaranteed error rate control, and we perform some level of detection delay analysis in our setting. So then, just to give you a brief idea of what our approach is about, well, most models for change point detection rely on parametric models, where the idea is to try to minimize maybe detection delay subject to a constraint on the false alarm rate, for instance, right? Here we follow a different paradigm, namely the estimation function approach that we adapt to network data. Mostly this method has been used for time series data, linear regression, or multivariate time series monitoring, right? But now we have graphs, and the basic presumption on this estimating function approach is that we have a training phase where we assume we have clean observations kind of before any change occurred, and then that's kind of reasonable in many contexts to collect data before you want to do any statistical inference, so that you can assume you have clean data. In this case, maybe you have M clean graphs, here 4 of them, which we can average and then obtain their ASC embeddings, let's say, in this training phase. Now, when we go and we average them, of course, to reduce noise in the embeddings and so forth. And now the idea is that when the monitoring phase starts, let's say from time n+1, n+2, up until an infinitely long horizon, what we do is we monitor very simply a cumulative sum statistic, right? Where the idea is that we track deviations that we aggregate, right, between the new graphs we observed, how do they deviate with the estimation of the matrix P we got from the ASC embeddings, right? And the idea is that if the graphs keep on coming from the same model, this will not drift too much in a way, because you have a good estimate of the mean of the distribution, right? Whereas if there's a model change, then you're going to see a drift, as you can see over here, right? So then we, at a very high level, and very informally, we were able, and then details are in the paper, you can check them, I can give you a pointer to that. We show that for a large K, large horizon, and then under the null hypothesis, well, the norm of this monitoring statistics has some generalized high square distribution, which we can characterize explicitly. And then the upshot for our online CPD procedure is that we can then come up with threshold selection rules that guarantee error rate control, because you have the quantiles and so forth. And for a given false alarm probability, you can pick a threshold that guarantees that the probability of a type 1 error is no more than alpha, say. And then here's a very simple toy example where an ergo-Shreni graph across time, a sequence of ergo-Shreni graphs, eventually switches at time 100 to an SVM graph with 2 communities. It's like a new community actually emerges, right? And here you can see the under the null distribution, the estimated in orange mean of the statistic, and here is the actual statistic that we are monitoring, so then it's kind of pretty close, and it starts to drift eventually when the change occurs. Of course, there's some delay because you have some inertia by looking at a lot of clean graphs, so then when you have changed graphs, it takes some time, and then you can play with the monitoring statistic to have a reduced memory to adapt faster if you want. And then we can pick a threshold, that's the dotted blue line over here, and then when the statistic crosses the threshold, we detect a change. And then you can see we can do it kind of with some delay, and that's compared, again, here the change in colors is the detection outcome for a batch state-of-the-art scheme that has much more complexity and can use all the graphs together. So it's not online. In this case, it gets the change spot on, whereas we incur some delay. We're going to see that necessarily is not the case in general. And again, a selling point of our approach is that this is very lightweight, right? The complexity is NV squared. You just need to sum matrices and store them. Let's say we don't have to keep the whole history, and then that's kind of nice. I'm going to skip this, but we have some analysis on the incurred delay. This is the delay as a function of where the change occurs. With the QSUM statistics, that's an infinite memory statistic. Of course, if the delay occurs later, then you expect to incur a longer delay, and we can predict that quite well. You can use different, maybe finite length windows, like the moving sum window. And in that case, even if the change occurs later, you can adapt much faster to it, as you can see, so you can play with that as well. And we have also some analytical characterization of what's the discriminability, right, or the detectability of the procedure that we are proposing here. When will we miss a change? When are you doomed? And well, again, details are in the paper, but just in a one-sentence high-level summary of the story, what we find is that, as you would expect, we need to have a small model perturbation to imperfection ratio. In a way, if the perturbation, let's say, we assume the model changes from an RDPG to another RDPG, and that's kind of without too much loss of generality because RDPGs are kind of expressive. If the delta in the change is kind of too small, the model doesn't change too much, well, it makes the problem more difficult to detect the change, right? So then that's the perturbation part in the numerator. Then on the other hand, we do estimation of the positions at the beginning, right? So then if you have little data or if it's very noisy, then you have higher imperfections there, and then that error propagates. And then if you have more imperfections in the denominator, well, that will make also estimation harder. So then these two play a role, and we have some probabilistic analysis of when can you expect that this condition will be satisfied, and then when can you get away with that for a particular setting. So then just to conclude, also going back to our rural area school back in Uruguay, then we tried our sequential change point detection procedure. If you remember, access point 4 was moved at some point in time. Actually, it was the 30th of October back in 2018. That's something that the administrator knew and told us as a cherry-picked example, but it's good to have a ground truth. And you can see that in this case, the model actually picks it up very, very fast, just 1 day delay, whereas the batch procedure in this paper, in this case, has more delay. For some reason, it doesn't work as well. And another nice thing of our approach is that if you look at, you can track, as we saw before, right, the positions of the different nodes, and then where do they move. And you can see, right, that if you look at something early in time and then something late in time, you can see that node 4 moved a lot. And then this doesn't give you an answer, but at least it tells you, okay, let's go and look carefully. Node 4 seems to be suspicious. And then if you ask, and then you went there, you will figure out that actually they moved it from one floor to the other one. So then that's all I have for today. We have a lot more data sets. You can run tests in dynamic social graphs, football networks, and you can check data sets as well as our codes for this online CPD routine. We're looking at characterizing the delay, now its distribution more formally with asymptotic analysis as m goes to infinity. And then maybe thinking about what if we want to detect changes when you're not given the graphs, but maybe only some graph signals that maybe relate to the graph through some diffusion model. Santiago Segarra and his students have been working on that in a different context, but the question is, can you obtain embeddings given graph signals only and then use them in this particular context? Well, we're looking at that. Sorry for the extra minutes. Thanks for your attention, and I'll be happy to address any questions if you have them. Thank you very much.
Thank you, Gonzalo. Very nice talk. Very interesting. Yeah. Application, kind of, I think, yeah, new in the graph signal processing field. So that's very nice to see. Let's see. There are some questions in the chat that recently popped up.
Yes, please. I did. I was not looking at those. Thank you.
Oh, they just popped up. So yeah. So the first is by Carson Fung. So I can read it, but Carson, if you want to unmute, you can also ask the question yourself. But up to you.
Yes. Anybody hear me?
Yes.
Yes. Hi. Thank you.
Yes. Thank you for the talk. Very nice talk.
Thanks.
You mentioned early on that using solving the MLE problem is intractable.
Mm-hmm.
So you switch to the least squares problem.
Yes.
And we know that least squares problem is not robust to noise. So have you thought about what happens when you need to find the embedding when the graph is not clean? And,
yeah, sure.
Maybe perhaps a PCA approach will work in this case.
Sure. Yeah, that's a very good question. Again, going to the first part, the MLE is hard, but it has very nice statistical properties. The ASC, which is an least squares based estimator, I just want to say, people have been able to show that, for example, is asymptotical in the number of nodes consistent, and also people have characterized a central limit theorem types of results for the embeddings. So then we have a probabilistic characterization, so the embeddings become Gaussian as well. I showed results that we derived in the weighted case. So then you have some nice statistical properties nonetheless when the number of nodes actually grow. The issue of robustness is something that they haven't explored too much. And then again, back in my PhD days, in the context of regression or other problems not related to graphs, I was very much interested into that. And of course, one can think of M-type estimators and so forth. For this particular case, if you have some heavy-tailed error distributions or what have you. Yeah, the problem is that in that case, somewhat, right, then you lose the nice spectral characterization of the solution. But nonetheless, based on the second part of my talk, I would argue, well, this doesn't matter too much. You can just have, if you have some smooth cost function, you have a factorization problem. So then based on iterative procedures, you may try to look at those solutions. The answer is, that's a very good idea. I don't know very much about results on robustness to outliers or other contexts, and then how it would compare to a PCA type of embedding. I don't know, but good point. Thank you. And then worth investigating more. I think one could think about M estimators or other type of, Hubbard type of loss functions instead of least squares to endow the embedding process with more robustness and then maybe solve them iteratively. That could be a good way to go, but I haven't looked at that myself. Thank you.
Okay, yeah, thanks. Then Said, do you want to ask the question yourself?
Yeah, thank you very much, guys. And hi, Mateos. Good to see you. Good to see you after a while, after we met in Belgrade, I guess we'd get all together.
Not too long ago then. Hi.
Yes. Well, I was thinking that the algorithms we provided much related on the distribution of the data in one way or another. And what happens when the data is not really long enough, when the data samples are not large enough, and how basically it can impact really these methods. Is there something you can comment on here?
Yeah, absolutely. Let's say these methods, again, even some of them and the change point detection procedures and approximations of our null distribution, whatever, for example, there we were saying that K has to be large to approximate things, but in a way like a Gaussian central limit theorems type of results will kick in anyways if you have a large graph, let's say. So then many of these results, consistency, asymptotic normality of these embeddings actually can be are derived asymptotically in the number of nodes. So then I would say that nowadays, right, we have more and more larger graphs. So then that's not something that can be hard to have. And in a sense, that's very nice, let's say, to have better approximations. But for example, I was showing you examples in a school with 6 nodes, right? So then the question is how robust are those to those limited sample data? When, well, you have some tail distributions, again, based on these limiting distributions for the embeddings, we have a Gaussian distribution. For the consistency, we have some limiting rates. So then again, with that, we can use some concentration inequalities to kind of have an idea at least of how far we are going to be if the number of samples you have is this versus that. So then with that, you can quantify clearly performance in terms of recovering the true embeddings is going to be hindered. But again, in most of our experience, and then as you can see, we worked extensively, and the nice thing that you can play and then get the nice results with real data, we haven't found this to be really an issue. Even for small graphs, you can still capture important rich structure in your data, even if the graphs are not huge. But still, statistical tools, which are nice, have been derived for these embeddings. And again, that's something I would argue is nice of this structure, maybe more model-based spectral embeddings compared to what you can learn maybe using a graph neural network. That's a different approach, valid. But then now sticking to this nice structure then allows you to have all these statistical tools that where you can say more of how things actually vary with the sample size and what have you. And I hope that to some extent addresses your question.
Yes, exactly. Thank you very much. Thank you.
My pleasure. Thank you. Good seeing you.
Thank you, Said. Any other questions from the audience? Just unmute yourself if you want to ask a question. In the meantime, maybe I can ask a question about in the beginning. So when you have this kind of distribution of the probability, so it looks a bit like what you have in graphons, right? That you have, that your adjacency is like a realization of some kind of graphon, and then you try to embed it. So is there some connection then? So because you have this kind of distribution, capital F, right, which you now usually you consider blocks
uniform 0-1, let's say that would be for a graphon. Let's say the graphon analogy will be like the function F could be anything in a way.
Right, could be, right. So that's what I was, what I was wanting.
That relates also more to what I was saying here of having a just more general latent position models where the link function could be anything. Then in graphons, right. Sorry to jump in, Gert.
No problem.
I didn't let you finish your question, but kind of the connection is that indeed this is kind of similar. This link function could be, it's what we define a graphon. Then in the graphon approach, typically the node representations are basically uniform in 0-1. So then the embedding space is like that. And then we go beyond, in a way, the inner product. Again, that induces some particular geometry here, which maybe is more interpretable if you want. But then in a way, all of these fall into the class of graph exchangeable models, which are known to maybe have some problems per se in terms of modeling sparse graphs when the number of nodes grows. And then with that, you can scale in a way, for example, the graphon function or our link function as well. So then the RDBG will have the same problem, let's say. So then you can scale the inner product as a function of n to render your graph sparse. But something that interesting that has been actually looked at very recently is that, as it turns out, if you have finite dimensional embeddings, finite dimension D, then you cannot have, even if you scale, you cannot have sparsity and transitivity at the same time. Let's say that's something that you would like to have in some context. And then just some very reasonable work said that, okay, actually pinned down that the problem is on having low dimensional embeddings. And then if you can think of inner products in infinite dimensional space, like we do in kernel PCA or what have you, then you can get away with it. And you can still do inference, because what you need is that these latent points actually live in some low dimensional manifold within high dimensional space. So then in a way, all of these are exchangeable models. Graphons are kind of a flavor of it, where the difference is that positions are uniform, scalar positions, uniform 0-1. And then you have the graphon is the linking function. I give you a particular one, given inner products. I work with vectors, positions there are scalars, and then all of them fall under the general class of vertex exchangeable models, which are
you would say that kappa is kind of the graphon, right? The graphon.
It is the graphon. It is the graphon indeed. Yes.
Yeah. Okay. Yeah, clear. Thanks.
Thank you for the question.
Any other question? If not, then I think we can close here. So thanks a lot, Gonzalo, for
thanks again for the invitation, and thanks to all that connected. And thanks for the questions. Yeah. Of course, just forgot to say, you can follow up if you have any questions. I guess you know where to find me. Happy to address any of those via email, and happy to share papers if you want to read more. Just feel free to reach out afterwards.
Yeah, and the video can be found on the YouTube channel of the Signal Processing Society website. So
yes, and I guess there you will also have access if you want to play with data and then try the CPD algorithms. Everything is here, and we're going to add hopefully soon also the dynamic estimation or embedding algorithms as well. We're just putting everything, cleaning it up, and it will be there as well eventually.
Okay, so thank you everyone. And we will see everyone hopefully in 2 weeks for